Hello and welcome back again. So, in the past few classes, we have been talking about this microstructure control in the atomization process. And so far, we have had a great deal of discussions as to how the microstructure can change depending on the process parameters in this atomization process. Now, what we have seen so far is that as far as the microstructure is concerned, we have seen this kind of microstructures, dendritic, and equiaxed, right? And the transition between these, that depends on the process parameters, as I said, and these process parameters are the cooling rate, the temperature or the thermal gradient, and also the undercooling. And in the previous class, I was mentioning that this microstructure control or this change of microstructure is not only between dendritic and equiaxed, there can also be a possibility of transition between a crystalline and an amorphous structure. And in the last class, I briefly told you as to what could lead to this transition between a crystalline solid to an amorphous solid as far as the process conditions are concerned. And we had seen that the cooling rate has a great influence in this particular transition. Okay. But before we proceed to this microstructure transition between crystalline and amorphous, at this juncture it is also important to understand what is crystalline and what is amorphous. So, for the benefit of everybody, especially people from non-metallurgy background, let me first briefly describe these two kind of structures, so that we have a better understanding of what we are talking about and what kind of transition we are talking about in this case. Okay. So, if you talk about a solid material, in terms of its internal structure, which is also referred to as the crystal structure, there are two kind of solid materials, two categories that the solid can be broadly categorized into depending on the crystal structure. One is crystalline, and another is amorphous. the crystalline material will have atoms arranged in a particular manner. Or in a particular pattern, and this pattern in fact can be defined by a small unit which can be then repeated in 3 dimensions to generate the entire crystal structure. For example, in a given material, the atoms may be arranged like this. So, in this in this 2D schematic, you can see that in both the directions, this distance, if we call that as A, remains the same. Let us say this is x and this is y direction. So, in x direction this distance repeats, okay, it remains the same. Similarly, in the y direction also the repeat distance will be same. If the material is a crystalline material with a particular crystal structure. Okay. So, therefore, this kind of structure can be defined by this one unit itself, where along x the repeat distance is a and along y axis the repeat distance is b. Okay. And this can be repeated in all the 3 directions. Now, if I add the z direction also, then in that direction also it is going to repeat with a particular distance between 2 adjacent atoms. So, on the x axis, on the z axis, this can be written as C, for example, right. So, this A, B and C, these are the 3 parameters which will repeat themselves in the x, y and z direction respectively. Okay. And this small unit, or the smallest cell that now we have constructed is known as the unit cell, which can be repeated in all 3 directions to generate the crystal structure, okay, or generate what we also call as the lattice. So, it can be repeated again, like as I said. and these distances along each of these axes will remain same as A, B and C. Okay. So, this kind of material is a crystalline material, and in this case you have seen that this unit cell has taken the form of a cube. Okay, where the atoms are in the corners of this unit cell. So, this is an example of a cubic solid or a cubic metal, let us say. Okay. So, like that metals can have other kind of crystal structure also. For example, they can also be hexagonal. So, in each of these kind of structure, the atoms are arranged in a particular pattern or in a particular order. Okay. And in most of the cases, the metals will have several of these crystals. So, a metal as such or a crystalline solid as such therefore can be defined as an aggregate of these crystals, right. And in that case, when you have several crystals together forming the entire structure, will be known as a polycrystalline material, okay, which is an aggregate of several crystals. Okay. So, this is what most of the metals are generally. They are polycrystalline in nature. Okay. And for a polycrystalline solid to form from the liquid phase, these atoms have to be sorted out in that particular arrangement when this solid crystal is growing from the liquid. Okay. So, just remember that we are going to come back to that as to how that is going to happen and what role the process parameters will have in that process of atomic sorting or atomic arrangement in order to form a crystalline solid. Okay. Now, the other category is the amorphous one. In this case, the atoms do not have any particular pattern of arrangement. Or in other words, atoms are arranged randomly. Right. So, these atoms, they may not have to follow any particular order like what we have seen in case of the crystalline materials. So, there is no repeating of any of these features or distances in a periodic manner. when the structure is amorphous. Okay. So, this kind of structure you will generally find in the common glasses that we see around us, and therefore, an amorphous structure is also known as a glassy structure, right. So, in terms of the atomic arrangement or the crystal structure as we call it, solids are of two types. One is crystalline and another is amorphous or glassy. Okay. And in a crystalline solid, as I mentioned before also, there are more than one crystal, making it a polycrystalline material. And the structure of a polycrystalline material can be defined by a unit cell which actually corresponds to a particular crystal structure or a particular lattice structure. We have seen the example of this cubic structure, wherein the atoms are in the corners of a cube like this, okay, which will give rise to a cubic metal or a cubic crystalline solid. There can be other variation on this, like for example, you can have atoms at the center of each of these 6 faces that you have, like this. And therefore, that kind of crystal structure will be known as face centered cubic or FCC in short. Okay. An example of an FCC metal is aluminum, or copper, which is also FCC. Okay. One more variation can be like this. Where apart from the corners, there is one more atom at the center of the body of this cube. Okay. And therefore, that is known as body centered cubic. or BCC in short. An example of a BCC metal is iron. So, like that in a particular crystal structure there could be different variations also like this, and depending on that a particular type of crystal structure or lattice will arise. And like that, like how you have in cubic, starting from simple cubic where only corners will have the atoms, you have FCC and BCC also. Similarly, in other kind of crystal structure, we will also have their own variations. Okay. Now, the original question in front of us right now is to how this crystalline structure can change to an amorphous structure in the liquid to solid transformation. And in this case, we are talking about this particular process, atomization, where the liquid stream, after it is broken into droplets, solidify as solid powder. Okay. So, during that solidification process, we are trying to understand as to how the microstructure can change, or what are the roles of these process parameters of this process on the microstructure, so that we can exercise some control on the microstructure and generate a particular type of microstructure which is needed for certain type of properties. Okay. So, that will be the main discussion with regard to this process that we need to understand. Okay. But for today, this is all I will have. And like we generally do before we close the class, let us try and summarize it. Today, we have discussed about the internal structure of a solid material, the internal structure or the crystal structure. And with regard to that, we have seen there are two types. One is crystalline or polycrystalline, where atoms are arranged in a particular pattern, which can be defined by a unit cell, which is the smallest unit that can be repeated in the 3 dimensions to generate the crystal structure. Okay. And the other one is amorphous, where the atomic arrangement is random. In this case, there is no particular order for the arrangement of the atoms. They are arranged randomly. So, there is no unit cell or no crystal structure that can be defined in this case, and this kind of structure is generally found in the glasses, and that is why this kind of material or this kind of structure is also known as glassy structure, right. So, this is what we have learned today in today's class, and going forward in the next class we are going to see how this crystalline can change to amorphous during the solidification process. So, today I am going to stop here. I will see you again soon. Thank you.